Hello, everyone. My name is Alphose Zingoni. I'm a professor at the University of Cape Town, South Africa. The title of my presentation is Dual-Purpose Concrete Shells. The aim of this work is to explore the simultaneous use of thin concrete shells for roofing and liquid containment. What has motivated this work? Thin concrete shells were once popular as long-span roofing solutions, but their use gradually declined as a result of the cost of formwork for curved surfaces. Using concrete shells for both roofing and liquid containment enhances their utility value, which offsets their higher cost of construction. We hope this concept of dual-use shells will revive the widespread use of thin concrete shells once again. Let us consider some configurations for dual-purpose concrete shells. Dual-purpose concrete shells can take the form of shells of revolution, shells of translation, or some other class of shells. Here we'll focus on three configurations where the components of the system are shells of revolution. Thus, the theory of shells of revolution may be used in the stress analysis. The slide shows a cross-section of a building whose roof system comprises a dual-purpose concrete dome and a dual-purpose conical shell roof. The circular dome serves as the roof of a large circular hall. The conical frustum serves as the sloping roof of a circular aisle that runs around the circumference of the hall. The space above the two shells, bound between the inner surface of the conical shell and the outer surface of the circular dome, serves as a shallow water reservoir. The next slide shows on the left a paraboloid of revolution that is connected to a conical shell at the base, with the lower region of the paraboloid being surrounded by the walls of the conical shell. The inner paraboloidal space serves as an exhibition hall for tall equipment, while the outer space serves as an annular reservoir. The paraboloid is a dual-purpose shell. On the right of the slide, we have a toroidal dome of parabolic cross-section. The interior of the toroid serves as a ring-shaped exhibition hall. The central enclosure, which lies outside the cross-section of the toroid, serves as a water reservoir. The inner region of the toroid of negative Gaussian curvature is therefore a dual-purpose shell. For these configurations, we can easily find the membrane stresses using the membrane theory of shells. A preliminary study has shown that hydrostatic membrane stresses dominate over self-weight stresses in the submerged portions of the shell, in that the stresses in these regions are predominantly compressive. The simplest way of reducing the likelihood of buckling in zones of high compression is to increase the thickness of the shell. Thickening was effected linearly with distance along the meridian of the shell from a minimum value of T equal to T naught at the water level to a maximum value T equal to Ts at the support level. To illustrate the effect of gradual shell thickening, here are the stress variations of a spherical dome with a radius of 30 meters and a springing angle of 30 degrees for values of Ts ranging from 0.3 meters to 0.7 meters. Clearly, gradual thickening of the shell with increasing hydrostatic pressure has the effect of countering the steep rates of increase of stresses as the support is approached. Here are the stress variations for a parabolic dome of a planned diameter 100 meters, height 20 meters, and surrounded by water up to a depth of 10 meters. With the thickness in the upper region maintained at 0.1 meters, the final thickness at the support is varied from 0.5 meters to 1.5 meters. We can see clearly how the thickening intervention moderates the stresses in the lower part of the shell. In this slide, we see the results of a paraboloid, a parabolic toroid rather, whose cross-section is 10 meters high and 10 meters wide at the base, and with a mean toroidal radius of 15 meters. The central water reservoir is 5 meters in depth. Now, let us briefly consider edge effects. We know that in the immediate vicinity of the shell edges, the actual state of stress will deviate from the membrane values owing to the existence of bending effects. The bending effect may be evaluated from the bending theory of shells. Taking into account the edge effect, here is what the actual pattern of stresses looks like in the case of the spherical dome fixed at the base. As expected, bending significantly alters the membrane state of stress, but the effect is generally localized to the edge zone. Reinforcement on both faces of the shell thickness will take care of these bending stresses. The thicker the shell at the base, the greater is the reduction in bending stresses at the support, but the wider will be the zone experiencing significant bending effects. Now, let us turn our attention to buckling behavior. A linear eigenvalue buckling analysis of the three examples was performed using the finite element program Abacus. Here are the meshes for the three shells: the spherical dome, the paraboloid of revolution, and the parabolic toroid. Here are the results for the first 5 buckling modes. For the spherical dome with TS equal to 0.7 meters, for the paraboloid of revolution with TS equal to 1.5 meters, and for the parabolic toroid with a TS value of 0.25 meters. Typical of shells of revolution, all buckling modes are characterized by a relatively high number of waves in the circumferential direction, but only one wave in the meridional direction, except for the parabolic toroid, which is 3 dimples in the meridional direction. Considering only the first mode, which corresponds to the lowest buckling pressure, eigenvalues and corresponding buckling pressures have been plotted versus TS for the 3 domes. Eigenvalues ranged from 6 to 62 in the case of the spherical dome, and from 5 to 30 in the case of the paraboloid of revolution. These values represent high factors of safety against buckling. Such high values also suggest that the shells will still be safe even after accounting for the possibility of imperfections. For the parabolic toroid, the negative eigenvalues are simply an indication that buckling only occurs if the loading is reversed. Positive eigenvalues only started emerging at very high mode numbers and are therefore irrelevant. In nonlinear buckling, analysis taking into account geometric imperfections has just been completed, but the results are not included in this paper. This study has shown that the likely size of imperfections will reduce the linear buckling pressures by only 20 to 60%. Thus, the shells would still have good margin of safety even after taking into account the possibility of imperfections. Here is a typical load versus arc length plot for the spherical dome, with images of the shell just before the peak, at the peak of the loading, and the 2 points beyond the peak. In conclusions, we may state that excessive stresses due to water loading can be controlled through gradual thickening of the shell over submerged regions. Such thickening is also highly effective in enhancing the buckling strength of the shell. The overall conclusion is that the concept of dual-purpose concrete shells is viable. It is hoped this finding will help revive the use of thin concrete shells for roofing once again. Thank you.